We're on part 4 of section 5.2, the definite integral videos. And with this next problem that we're dealing with, we're going to use some of the properties of integrals that we talked about on the previous video. These properties where 1, 2, 3, 4, and 5. So you may want to keep them handy in your notes. So we have the integral from 0 to 4 plus 3x dx. So what we're going to do first is we're going to split the integral from 0 to 1 of 4 dx plus the integral from 0 to 1 of 3x squared dx. And this is taking time to discuss some of the rules that we have. So this rule that I'm using now is rule 5. You can refer to that later, where we took the integral of a sum and we have now the sum of two integrals. So then we're going to take the first integral and we're just going to say, well, that's a constant 4, so we're going to say that this is then going to be equal to 4 times b minus a, or 1 minus 0, plus, then we're going to pass the constant through 3, and that'll be 3 times the integral from 0 to 1 of x squared dx. So now in a previous lesson, we're going to say this is 4 times 1 plus, in a previous lesson we found that the integral of x squared from 0 to 1 had a value of 1/3, so we're going to use that for this lesson. So 3 times 1/3, and then we're going to combine, we're going to add that, we get 4 plus 1. So the integral has a value, the integral of 4 plus 3x squared dx from 0 to 1 has a value of 5. Okay, and let's just specify for a second here what I'm using here. This is rule 3 here, and then over here this is rule passing the constant outside. That's going to be rule 2, I believe. Okay, so now in the next example we're going to use the rules where we have a total area, and it looks like we're going to break it in 2 regions. So if I look at the rule, it goes like this. If I have a function that's continuous, so you're thinking f is continuous, and it goes from a to b, but there exists a c somewhere in between, then we have these rules where if we go from a to c, and then c to b, and took 2 integrals of the same area, we'd have the integral from a to c plus the integral from c to b of f of x dx would then be equal to the integral from a to b of f of x dx. This is on page 335, a rule, complete rule, and with all the conditional notation on that. Page 335, Stewart's 5th edition. So what we want to do with this is take our example 7 up here and then say if it's known that the integral from 0 to 10, so we're going to take the integral from 0 to 10 of f of x dx is then equal to the integral from 0 to 8, from 0 to 8 of f of x dx, plus the integral from 8 to 10 of f of x dx. I'm looking at that, I already have these integrals set up, and I have values for some of them. And it looks like on the left-hand side, this is 17 is equal to, from 0 to 8, that's equal to 12. But I want to find this last integral from 8 to 10 of f of x dx. So I just plug in the values, really. So I have 17 minus 12, which is 5, which will give us the value of the integral from 8 to 10 of f of x dx. So the integral has a value of 10. Oh, by the way, there's a lot of money in math, so if you're interested in that, there's the Riemann hypothesis. You can solve that. You can take a look on Google and see what they're offering for that. So now, comparison properties for integrals, and you will find these on page 335 also in Stewart's 5th edition. So if you would copy these down in your notes, so you can see the first one, if f is greater than 0 and a is less than or equal to x is less than or equal to b, then you have the integral from a to b of f of x dx is positive. It's greater than 0. So that's really what that's saying. If the function is positive, so is the area, so is the integral. So the second one says is if f is greater than g for a all the way through a to b, then the integral of f of x is bigger than the integral of g of x on the interval from a to b. Interval, marbles. Then the last one is just a comparison property that if you're going on the interval from a to b, then if you take a look at my color coding, that you see that if we have a small rectangle that hits the bottom of the curve, let me see if I can get an arrow. So if you have the curve flowing through here, oops, got the rectangle there. If you have the pink curve flowing through, and you see a minimum value on the pink curve is at lowercase m, and the maximum value is at the uppercase m, then we would have the area of the rectangle in light blue would just be m, lowercase m times b minus a. The yellow rectangle, just outlined in yellow, would be uppercase m times b minus a, the area of the rectangle, in other words, based on height. And the integral has to fit somewhere in between there. It kind of makes sense, right? The area of the small rectangle is less than the area of the large rectangle, of course, and you have the integral that fits in right between. We are going to look at that to use the comparison property 3 to estimate the value of an integral. And sometimes, though, we can integrate this integral. Other times you can't, and this becomes a very useful procedure. So you look at the graph and you say, okay, we have the maximum value is 2, so m is 2 at the top of the graph, so you may want to stop your video and mark this. And then the lowercase m, or the minimum value on the interval from 1 to 4 is 1. So we can say that the minimum value then is 1 times 4 minus 1 would be less than or equal to the integral of the square root of x dx from 1 to 4, which would be less than or equal to the maximum value, which would be 2, times the difference in the interval 4 minus 1. And then we would know by an estimation that 1 times 3, or 3, has to be less than, we'll put dittos here, has to be less than or equal to than 6. So we would know that the integral value, you can see my ditto marks underneath there, this has got to be in between 3 and 6. Well, if we know it's in between 3 and 6, let's see what the exact value is using your calculator. So let's put this here from 1 to 4 of square root of x dx, and let's see what it's actually equal to. So go to the calculator, put in y equal, put in the square root of x, and then go to your graph, take a look at your graph. I also note that I have a window that looks like this. X min -2, x max 6, and the y min of -2, a y max of 6. And then graph your function, and we'll do the same thing we did in a previous lesson where we're going to use the calculator to find the value of the definite integral. So we hit second, trace, 7, and we'll say the lower limit is 1, enter, and the upper limit is 4, enter, and we get the shaded area, and it turns out to be 4.6 repeating. So we'll go back to our notes and we'll say 4.6 repeating, 4.6 repeating, and of course it's 4 2/3, which matches the value that we're talking about being between 3 and 6. That's the last video. You do have an extra practice to do at home, but this is the last video in the 5-2, the definite integral. And the next lesson will be on the fundamental theorem of calculus. So I would probably suggest that you take some time and read over FTC, the fundamental theorem of calculus. It starts to really get exciting here. I love that we're working with inverse operations at this point. Also, this homework will be classwork. We'll be working on that in class. See you later. Looking forward to it. Take care. Please don't be too big.